Hello everyone, so today we're going to be going over the various ways you could explain the diffusion coefficients in a vapor-liquid binary mixture and how the Vignes formula is used in conjunction with the Einstein-Stokes equation and why is this necessary. So to start, we're going to first define our driving force, DAB, is equal to 0.00216 times temperature raised to the 1/2 power, so indicate that over 3/2, and divided by the molecular weight of this AB amount, pressure, the collision integral, and then the Leonard-Jones size parameter of AB. So, where are we getting these values? To start, our pressure, temperature, molecular weight we can find through experimental data. So that we can find on our own. Our Leonard-Jones size parameter is a little different. We got to find that from like a table that we find online for a specific material or whatever that we're using. For our collision integral, we got to be able to use some different equations to find this. So to start, our collision integral is equal to that's t powered plus exponent, so an exponential like e to the d times temperature O plus this E1 times another exponent of temperature S times F, and plus our last amount G, and then another next e to raise to the power of Ts times H. So this A, C, D, E, F, G, H can all be found through constants on a table. And obviously our temperatures, we derive that through our given data that we find in our equation. So now we have all the materials to get that driving force of AB. So now we can try to find that the TS. So what is TS here? Okay, that's still kind of a mystery here. And it's used a lot in this equation to find our collision integral. So again, just to reiterate, the A through H values are constants that are going to be derived for this experimental data. And then this TS will actually be the Boltzmann constant K times absolute temperature divided by the Leonard-Jones interaction parameter for AB. So write that down over here just so you remember it, because I know it's a little bit more complex. We're not super familiar with it. This is Leonard-Jones interaction parameter. So now for liquid we can do the following. We have our driving force of 1, 2 is equal to our Boltzmann constant, our absolute temperature, again it's very similar to that TS over there, and then times 6 pi, our liquid viscosity times our reduced radius. So this is again for our strain equation. So I should draw like a little line. And this helps us derive the Vignes formula. This is connected to that, which gives us this D112 is equal to, or driving force of 1 and 2 multiplied by our diffusion coefficient of D21, and then times our mole fraction of X1. So now what we can do is we can set these two equations equal to each other. So we have a Boltzmann constant times our absolute temperature, 6 pi times our our liquid viscosity times our reduced radius, and that's equal to our diffusion coefficient of 1, 2 times the mole fraction of the second system times our diffusion coefficient, and our our mole fraction of x1. So now setting these two equal to each other allows us to interpolate a system for like a more concentrated liquid. So thank you very much. Hello everyone, so today we're going to be deriving the equation continuity of component diffusion into a unidirectional system with a rate of formation of Ra. So to start, we're going to have this cube here, and we're going to envision this, our molar flux of Na entering into this cube, and then leaving this cube as our molar flux of Na plus dz. So how are we getting that dz? So first we gotta exemplify what our volume is. So we'll have dx, dy, dz. So again, it's going to that surface of dz right there. So it's Na plus dz. So now, it's important that we implement our volumetric rate of components of A, which we can associate with this Ra. So first I'm going to define this. So now let's turn this into an equation. So we have Ra times our volume of dx, dy, dz, because again, we're using the volume of this cube. And then we have that plus our Na, so our driving force. And that driving force is going through the values of dy, dz. So that's our area. Minus our Na plus dz, and times, again, our area, which is dx dy. So these, again, are area. This is our volume. And it's all going to be equal to our change in concentration of A, and then times our volume, dx dy dz. That's divided by our change in temperature. So to recap, we have volumetric rate of components A times our volume times, or then plus our molar flux of times our area of A, so our input, and then minus our molar flux of Na plus dz, or molar flux leaving, and then again times the area, and then it's equal to the change in concentration of A times volume, and then divided by our change in temperature. So this equation right here can actually be simplified a little bit further to make it a little simpler on us. To start, we find a common component of dx dy in all four of our formulas, so we're just going to get rid of that altogether. So now we have Ra times dz plus Na minus Na plus dz, Na of dz, and then times our change in concentration of A, dz, divided by our change in temperature. So now what we want to do is we want to get rid of that dz as well, but kind of getting rid of the dz. So if we were to divide this out, we have Ra plus Na, and this will be a common denominator of Na plus dz, all over dz. And then this gets canceled out, so we have delta C, the change in concentration times the change in temperature. So now what we see here is we actually see a change in our, from beginning to end of our molar flux. So this is really just a derivative. Now let's clear that other side, plus our negative derivative of Na plus gz minus our change in concentration of A, that's equal to 0. So this is our equation. So again, just in case I don't think I really explained it all that well, but because that's from the initial position to the ending position, it's actually a negative derivative instead of a positive derivative, just for a little clarification on that. So that's our final equation for continuity of components of diffusing into a unidirectional system with the rate of formation of Ra. So thank you very much. Hello everyone, so today we're going to be explaining that equimolar counterdiffusion arises at a vapor-liquid interface when the enthalpy of vaporization is independent of composition. So to start, we're going to have our vapor bubble of our interface. Our vapor bubble, we'll remember this YA. And then over here, we have our gas, or a liquid, excuse me. And right at this point is our interface. At this interface, this is actually in equilibrium. That's a key factor to note here at this interface of these molecular compositions are actually in equilibrium. So, when a molecule evaporates, it actually absorbs the enthalpy of vaporization. So, we can then quantify this through an equation. The molar flux times the enthalpy, the molar composition of Ya, or our gas, and then times our change in enthalpy. And we can add that to same thing with our molar flux, our gas composition, our liquid composition, excuse me, times our change in enthalpy. That's equal to 0. NYA delta H is equal to negative NXA delta H. So these delta H's can cancel out to where we get our molar flux times our composition of our vapor times our negative molar flux of our liquid. So this kind of just quantifies that the opposing molar fluxes of each other will actually oppose each other in a negative fashion, where the negative of the liquid is equal to the positive of the vapor in terms of the molar fluxes. So this kind of explains that the enthalpy of vaporization is pretty much independent between these two molar fluxes. So thank you very much. Alright everyone, so today we're going to be exploring the reaction of A getting converted to B on a catalyst surface. How is the total molar flux of N related to Na? And what's this relationship of 3A is being converted to B? To start, we have our reaction of A getting reacted to 2B. So we can start with our what our molar flux relationship looks like here in this relationship, which looks like N of B is equal to negative 2 Na. So this is our molar flux balance that we have here. So if we recall, NB plus Na is equal to N, which is, again, our total molar flux value. So let that focus on it a little bit. So what this allows us to portray is that now we can insert this NB amount for this negative 2 NA. So NB is negative 2 NA plus NA is equal to N, which gives us negative NA is equal to N. So it's the inverse negative amount of that total molar flux N. So now looking at our other side, that 3A being converted to B, molar flux relationship in this. So our molar flux relationship, or our molar flux balance, is NB, our molar flux of component B, is equal to negative 1/3 NA, or molar flux of NA. So again, we're going to reference our total molar flux relationship, which is just NA plus NB is equal to 1. So now we can insert that negative 1/3 NA into the NB amount, where we get NA plus negative 1/3 NA, which is equal to 1. So that gives us 2/3 molar flux of our component A is equal to our total molar flux of N. So you can see, very different, where in this initial one we have an inverse relationship, where here we have more of a 2/3 of our molar flux of component A is equal to our total molar flux. So thank you very much for listening.